want to get condition coverage possibly, but you also want to get multi-condition coverage. And multi-condition coverage is saying, I want to test every possible combination. So in condition coverage, we say, go back to the previous example, both A greater than B and C greater than D had to be both true and false. But in multi-condition coverage, we say, no, we want to test all 4 combinations. We want to test true, 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 false, false, true, and false, false. So that's what's happening there. You're testing all possible logical combinations. And since it's going to be defined on something that's Boolean, then it's the number of tests is going to be 2 to the power of however many atomic conditions there are. So either 4 or 8 or 16, what have you. Now, in multi-condition decision coverage, we back that down a little bit and we say, well, some of these condition combinations cannot actually affect the decision that occurs. So, for example, and we talk about if A greater than B and C greater than D, if the first condition, the A greater than B, evaluates to false, then most optimizing compilers will simply stop execution, and it will not check the second condition because it doesn't matter at that point. The overall condition has now been evaluated. It's going to be false and compound with an and. So instead of having to test 4 combinations in these situations, you would test 3. You would only test those combinations that would actually result in some evaluation of the subsequent conditions. So if you got to the point in the evaluation of conditions where any subsequent condition could not affect the decision, then you stop evaluating. And then finally we have loop coverage. Now in loop coverage, ideally you would try to cover all possible loop paths, but that's generally impossible. So usually the idea is to cover 0 loop paths, in other words, not executing the body of the loop at all. Once, in other words, executing the loop body exactly one time, once and only once, and then multiple times, and ideally that would be the maximum number of times. Now, in some cases the maximum can be squishy, if you will, because the program is looping on some sort of condition that's determined by the real world, and then it can go on, for forever, basically. I mean, for example, like event-driven programs, they just sit there in a basically infinite loop, waiting for events to occur until something causes them to terminate. So, how many events can Word, for example, respond to in the course of a single usage session? Well, it's not really possible to say. But in loop coverage, we would want to get a very large number of loop iterations, something that would potentially be stressful to the system. So let's take a look here. We have a simple example here. As one of you noticed at the very beginning of this presentation, is the Fibonacci program here, or a Fibonacci program. It generates a Fibonacci series using a loop. So we're going to ask first for the number of elements, and we're going to read that in, and then we're going to, if the number of elements requested is invalid, we're going to give an error message. Otherwise, we are going to print the Fibonacci series inside of a pair of curly braces, and it's going to loop around and generate the elements of the series and print them out one after the other, and then it'll exit. So in order to get statement coverage, notice that if we test with n less than 0 and n greater than 0, we will execute every one of the statements. So if we take negative 7, for example, let's go ahead and highlight this. So if we take negative 7, then we go here and we get this, and do that piece there, and then since we're less than 0, we're not going to do the body of the else, so we're going to go down here and we're going to exit, and out we go. Now, if we then test with, say, 2, we would come in here again, and we cover this again, we get here, and then we go, okay, we're going to do the else. We come down here, and we loop around this loop a couple times, and then we exit, print out, and then we exit. So as you can see there, every statement got painted, if you will. Now, the question next here is, well, did that get us branch coverage? And there's a little bit of controversy about this, but my answer is no. My answer is that you would have to test with n equals 0 to also get branch coverage. Now, why do I say that? Well, it's because basically a loop has to be thought of as a form of a branch. It is an interesting form of a branch where it is directing the control flow back upstream as long as certain conditions are met. And then if not, it's directing the control flow around the loop body to the subsequent code if those conditions are not met. So it is a branch. It's just a branch that happens to iterate its body. And it's also, if that's not a convincing enough argument to you, for those of you who've gone through a computer science program, think about how the loop is ultimately implemented in the assembly language down at the guts of the computer. I mean, it is basically the same mechanisms by which a branch is created. There's no difference. So since what we're trying to do is test the program based on the way the program actually works, since a loop is implemented using the same constructs that are used to implement a branch, it seems to me nonsensical to argue with branch coverage doesn't apply to loops, though you will sometimes see people making that statement. Anyway, my opinion is that you would have to test with n equals 0 to not test the body of the loop once in order to get the branch coverage. Now, will this get us condition coverage, multi-condition decision coverage, multi-condition coverage? Yes, in this case it does, because there are no compound conditions. So you have to have compound conditions for there to be a difference between branch coverage and condition coverage and multi-condition coverage and so forth. Now, in terms of loop coverage, notice that we would have to test with n equal exactly 1 in order to test that. Since that's a greater than 0 value, then we could use that instead of, say, 2. And n equals some maximum. And then the maximum is going to be determined for this particular program by either a requirements specification, ideally, what's the maximum length Fibonacci series that this thing can generate, or in default of that, it will be determined by the point at which the integer values overflow. And for one of those, at some point or another, that integer variable c will overflow, and that will stop the program. Of course, it's extremely bad programming practice to rely on some sort of internal mathematical overflow error to terminate the program. So that, I would say, that is definitely a bug. So in the absence of any stated maximum, then one should test this all the way up into the point where it does overflow, and then you would file a bug against that. Okay, so let's take a look at condition coverage a little bit more closely here, just to try to clarify the point I was making a moment ago. Get my highlighter going here. So if we look at lines 1 through 5 here, these guys, if we say condition coverage, we want condition coverage, then we have to have true, false, and true and false. Right, now notice that conceivably this could be done with just 2 tests. You could have true, true, and you could have false, false, all right? Which is, of course, exactly the same as what you would need for branch coverage or decision coverage here. Multi-condition coverage, then it would be, as I said before, true, 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 false, false, true, false, false. So we've got 4 tests. And then multi-condition decision coverage, it's true, 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 false, and false don't care. They can be either true or false, so there's 3 tests. Okay, now let's look instead at lines 7 through 11, because this is an interesting possibility here. And now notice here we're checking to see if this value f is not null, and then we're checking to see what it points at. Okay, so apparently f is a pointer, and we're checking to see if the value that it's